The Big Bang was not the beginning. It was the aftermath, the smoke, not the spark. We were taught that everything started from one point of infinite density, but the universe we observe is too smooth, too flat, too vast to have begun that way. Something came before, something colder, something stranger. A silent expansion with no flash, no heat, no bang. If we want the true origin of reality, we must step behind the curtain to a moment before time ignited, where space inflated faster than light, and perhaps still does. Clear your mind, because this is where the story really starts. And if the beginning was not the Big Bang, then what universe are we actually living in? To understand what came before the Bang, we must first understand how we arrived at the belief that the Bang was the beginning. The mistake did not appear overnight. It was built slowly, layer by layer, through centuries of reasoning that once seemed unbreakable. For generations, we were taught about the singularity, a point of infinite density at the beginning of time. It sounded clean and logical, yet it is almost certainly incorrect. Inside modern cosmology, this shift has already happened. Most physicists no longer see the Big Bang as the true beginning. The singularity is now viewed as a mathematical failure, a sign that our equations reach their limit, rather than a real state of nature. This is not a defeat. This is how science moves forward. Astronomy is a graveyard of ideas that once seemed perfect until evidence overturned them. People believed Earth was the center of everything. Later, they thought the Milky Way was the whole universe. For centuries, they even imagined the cosmos as eternal and unmoving. So we must ask, how did models so flawed survive for so long? Why did brilliant minds defend them? Why did logic bend to preserve an idea that could never last? If we want to understand the multiverse, we cannot skip the mistakes. We must trace the story back before the Bang to the first model that shaped our thinking. We return to the year 1687. When Newton published the Principia in 1687, he unified the heavens and the earth under one law. The same force that pulls an apple downward holds the moon in orbit and keeps the planets in motion. It was a triumph for physics, but it carried a hidden problem. If gravity acts everywhere, then everything with mass should pull everything else closer. A universe full of stars should not remain spread out forever. Like a ball that must fall back to Earth, the cosmos should collapse under its own weight until all matter merges into one. Newton understood this danger, so he proposed a way out. He claimed the universe must be infinite in size and eternal in time. With matter distributed endlessly in every direction, each star would feel an equal pull, preventing collapse. For centuries, this picture became our cosmic foundation. But the stability was an illusion. Solving gravity created a new contradiction. An infinite universe filled with stars leads to a very different outcome. There should be no night at all. Picture yourself inside an endless forest. Nearby trees may leave gaps, but farther out they overlap until every direction becomes wood. Replace trees with stars, and the result is unavoidable. If stars fill infinite space, then every line of sight from Earth must eventually hit one. The sky should shine as brightly as the surface of the sun. Space would blaze with heat, and no darkness would exist. This is Olber's paradox. The night sky is dark, therefore, Newton's universe cannot be both endless and unchanging. Either light has not had time to reach us, or the universe is stretching and pushing starlight beyond visible wavelengths. In either case, a static, eternal cosmos is physically impossible. The model that felt safe had already failed. A new idea was needed to escape this trap, and just a few decades later, two men would change everything. In 1915, Albert Einstein gave us a new vision of gravity. His general theory of relativity showed that gravity is not a force, but the curvature of space-time. Applied to the entire universe, the equations predicted motion. The cosmos could not remain still. Einstein resisted that conclusion. To hold the universe in place, he added a term to his equations called the cosmological constant, a mathematical patch used to freeze a living system. It delayed the truth, but could not hide it forever. While Einstein tried to stop the universe from moving, Henrietta Leavitt was studying a class of stars known as Cepheids variables. These stars brighten and dim in perfect rhythm like cosmic clocks. Their pulses revealed something extraordinary. The length of each pulse is tied to the true brightness of the star. Measure the rhythm and you know its distance. For the first time, we had a way to map the cosmos. In the 1920s, Edwin Hubble used Leavitt's discovery to examine distant nebulae. He found that many contained Cepheid stars. They were far too bright and too far away to belong to the Milky Way. They were entire galaxies separated from us by millions of light years. Then came the breakthrough. Hubble compared these distances with Vesto Slipher's observations of starlight stretched toward the red end of the spectrum. Redshift meant motion. The farther the galaxy, the faster it moved. When Hubble plotted the data, the universe itself was running away from us. The static model collapsed. Einstein would later call his constant a mistake. The universe was not fixed in place. It was growing. And if it expands today, it must have been smaller yesterday. Reverse time far enough and everything once existed in a single, dense state. The age of a silent, expanding universe had arrived, but the victory was only surface deep. The next discovery would show that even the Big Bang could not answer everything. If the universe is expanding, then running time backward gives a single conclusion. Galaxies converge, distances shrink, temperature rises. Everything that exists is squeezed into something smaller than an atom. In 1927, Georges Lemaitre proposed this bold idea. He called it the primeval atom. The universe, he suggested, was the cooled ash of a violent beginning. A single moment ignited everything. Many scientists rejected it. Einstein disliked it. Fred Hoyle ridiculed it publicly and promoted the steady-state model instead, a universe without origin creating matter endlessly to fill the growing space. His insult on air, calling it a Big Bang, became the name of the theory he opposed. Debates do not decide science. Evidence does. If the universe was once hot, some of that heat must remain stretched and faded, but still present. To find it, we must picture the universe long before stars existed. 380,000 years after the beginning, everything was plasma. Electrons and protons drifted apart in a brilliant fog too hot for atoms to form. Light was trapped. Photons scattered off free electrons again and again, unable to move in straight lines. The universe was bright yet opaque. As expansion cooled space, it reached a critical threshold near 2,700 degrees Celsius. Electrons settled into orbits around protons. Neutral hydrogen formed. The fog thinned. Light escaped for the first time. The universe went dark and transparent, lit only by the fading red glow of its own release. That light never stopped traveling. Over billions of years, expansion stretched it into microwaves. It still surrounds us now as a faint background signal. In 1964, Arno Penzias and Robert Wilson detected an unexplained hiss in every direction. They cleaned their antenna, even removed pigeons nesting inside, yet the noise remained. They were hearing the afterglow of creation itself. The cosmic microwave background. Steady state collapsed. The Big Bang stood. We had finally found proof of a beginning. But when physicists examined that ancient light more closely, something unexpected emerged. The Big Bang answered how things began, yet the details of the CMB revealed three problems the theory could not solve. And to face those problems, we must break open the Big Bang itself, not to destroy it, but to expose the cracks hidden beneath its triumph. The discovery of the cosmic microwave background should have been the end of the story. The Big Bang was confirmed, the smoking gun was found. But as physicists scrutinized the baby picture of the universe, the celebration turned into unease. The math of the standard Big Bang model, despite predicting the expansion, contained three fatal logical flaws, three paradoxes that suggested our understanding of the beginning was fundamentally broken. The first is known as the horizon problem. When we look at the cosmic microwave background, we see a miracle of uniformity. Whether you look at the far left of the universe or the far right, the temperature is almost exactly the same, 2.725 Kelvin. The deviation is less than 1 part in 100,000. Under the laws of thermodynamics, for two regions to have the exact same temperature, they must exchange heat. They must interact. But in the standard Big Bang model, this is impossible. Imagine 2 points on opposite sides of the sky. 13. 8 billion years ago, light began traveling from both of them toward us. But light has a speed limit. There has not been enough time in the history of the universe for light to travel from point A to point B. They are causally disconnected. They have never met. They have never exchanged information, yet somehow they have the exact same temperature. It is akin to finding two strangers on opposite sides of the Earth who have never communicated holding cups of coffee that are identical in temperature down to the millionth of a degree. Coincidence does not explain this. Something is missing. The second paradox is even more disturbing. It is known as the flatness problem. This question comes down to the shape of space-time itself. Scientists describe it using a single value called omega, which represents the total amount of matter and energy in the universe. If omega is greater than 1, the universe contains more mass than it can support. Gravity becomes dominant, space bends inward like the surface of a sphere, and over time, the entire cosmos collapses in a final big crunch. If omega is less than 1, there is too little mass to slow expansion. Space bends outward like a saddle, and the universe spreads apart forever, until everything dissolves into a cold and empty darkness. But if omega is equal to 1, not higher and not lower, then space-time becomes perfectly flat. It does not curve inward or outward. Parallel lines remain parallel for all eternity, neither converging nor drifting apart. When astronomers measure the universe today, the value of omega is shocking. It is exactly 1, with a margin of error of just 0.4%. This sounds convenient, but physically, it is a nightmare of probability. The value of omega is unstable. As the universe expands, any tiny deviation from perfection grows exponentially. If the universe started with an omega of 0.99999 at the beginning, it would be close to 0 today. If it started at 1 versus 1, it would have collapsed billions of years ago. To find a flat universe today, the initial conditions of the Big Bang must have been fine-tuned to an accuracy of 1 part in 10 to the 60th power. To visualize this impossibility, imagine a sniper trying to hit a target at the edge of the observable universe, 46 billion light-years away. The target is not a planet or a star, it is a single coin. If the sniper's aim deviates by a fraction of a specific atom, they miss. The standard Big Bang model asks us to believe that the universe, by pure random chance, hit that coin. Physics does not believe in luck. This precision implies a mechanism we are not seeing. The third paradox is the monopole problem. High-energy physics predicts that the extreme heat of the early universe should have created massive, stable magnetic particles, called magnetic monopoles, magnets with only a north or a south pole. According to standard theories, these relics should be as common as protons. They should be littering the cosmos, weighing it down with their immense mass. Yet we have never found one, not a single trace. They are completely missing from the picture. We see no trace of them anywhere. These three paradoxes, the uniform temperature, the impossible flatness, and the missing relics, pointed to a devastating conclusion. The Big Bang, as a singularity, was not the beginning. It was missing the engine that set these conditions. The universe needed a prequel. If the Big Bang could not explain the uniform sky, the perfect balance of space-time, or the absence of relics, then the answer had to come from somewhere earlier. In 1979, a young physicist named Alan Guth realized that the solution lay in the vacuum of empty space itself. He found the spark that didn't just cause the bang, but engineered the universe before it even began. The answer to the paradoxes did not come from looking at the stars. It came from looking at a glass of water. And then came the moment everything shifted. In late 1979, a young particle physicist named Alan Guth was working late into the night, obsessing over the physics of phase transitions, the moment matter changes state like steam turning into water, or water freezing into ice. He was fascinated by a phenomenon called supercooling. If water is pure enough and still enough, you can cool it below 0 degrees without it freezing. It stays liquid, trapping its latent heat energy inside, waiting for a trigger. It is a state of unstable, pent-up potential. Guth realized that the early universe might have done the exact same thing. He proposed that in the fraction of a second after the beginning at 10 to the minus 36 seconds, the universe didn't just expand, it supercooled. It got stuck in a state known as a false vacuum. To visualize this, imagine a ball sitting at the bottom of a valley. This is a true vacuum. stable low energy. Now imagine that ball sitting on top of a high plateau perched precariously on the edge. This is a false vacuum. The ball is motionless, but it possesses immense potential energy, simply because it is high up. It wants to fall, but it can't. Not yet. In this high-energy state, the laws of gravity flip. Instead of attracting, the vacuum pressure becomes negative. It creates a repulsive force, a gravity, that pushes, and it pushes hard. Guth calculated what would happen if the early universe got stuck on this plateau for just a fleeting instant. The result was a spectacular realization. The repulsive gravity would drive an exponential expansion of insane proportions. In less than a trillionth of a second, the universe would double in size, then double again and again, expanding by a factor of at least 10 to the 26th power. This was not an explosion of fire. It was an explosion of space itself. It was silent, cold, and dark. Space stretched faster than the speed of light, ripping coordinates apart. A region the size of a subatomic proton was instantly stretched to the size of a grapefruit, and then to the size of a galaxy. This event is called cosmic inflation. In a single breath of cosmic time, the universe transformed. And with that transformation came the answers the Big Bang alone could not give. This sudden expansion provides clear answers to the three major inconsistencies left by the Big Bang. The horizon problem. Why are opposite sides of the universe the same temperature? Because before inflation, they were touching. They were in thermal contact, swapping heat in a tiny subatomic embrace. Then inflation ripped them apart faster than light, flinging them to opposite ends of the cosmos, freezing that shared temperature into place. The flatness problem. Why is the universe perfectly flat? Because inflation stretched it. Imagine a wrinkled raisin. If you blow it up to the size of the Earth, the surface looks perfectly flat to anyone standing on it. Inflation stretched the fabric of space-time so violently that any initial curvature was smoothed out to the precision of that impossible sniper shot. The monopole problem. Where are the magnetic monsters? They are still there, but inflation diluted them. If there were 1 billion monopoles in the early universe, the expansion scattered them so widely that there might be only one in our entire observable horizon. But the most terrifying and beautiful moment is how it ended. Inflation could not last forever. The ball eventually had to roll down the hill. The inflaton field, the energy field that powered this expansion, began to decay. Then came what physicists call the graceful exit, a final and violent release where all stored potential energy flooded into the newborn universe at once. This event is known as reheating. The energy of the vacuum converted instantly into a boiling soup of particles and radiation. The cold, dark, expanding void suddenly ignited. This was the fireball. This was the moment we call the Big Bang. The standard story got the order wrong. The Big Bang was not the beginning. It was the aftermath. It was the heat released when the engine of inflation finally turned off, and it left a scar. Inflation was driven by quantum fields, which are never perfectly still. They jitter with quantum fluctuations. When space expanded faster than light, these microscopic jitters were caught and stretched across the cosmos. The tiny lumps in the density of the universe today, the seeds that gravity would later sculpt into galaxies, stars, and planets, are nothing more than fossilized quantum static from before the bang, frozen into the sky like a photograph of the moment of creation. The galaxies, stars, and even we ourselves ultimately formed from the tiny quantum ripples in that early vacuum. But if inflation can happen once physics suggests a haunting possibility, it might not have stopped everywhere. And if it did not stop, then our universe may be only one outcome among many, a single spark in a much wider fire. If inflation is the engine that created our universe, then we are left with a final dizzying question. Did the engine turn off everywhere? The equations of quantum mechanics suggest the answer is no. Recall the ball rolling down the hill, the energy field losing height and releasing enough energy to ignite the Big Bang. In the quantum world, nothing is exact, nothing sits perfectly still. As the field rolls downward in one region, quantum fluctuations may nudge it upward somewhere else. Inflation ends in one place and continues in another, stretching space even faster and pushing those distant regions beyond any path we could ever reach. This leads to a model known as eternal inflation. Imagine a vast boiling ocean of energy. This is the inflaton field. Most of the ocean is expanding violently forever, but in random spots the energy cools down and drops out of the expansion, forming a bubble of stable, normal space. Inside that bubble, a big bang occurs. Stars form. Galaxies spin. Life evolves. We are living inside one of these bubbles, but we are not alone. Far beyond our cosmic horizon, separated by expanding void that exceeds the speed of light, other bubbles are forming. Other big bangs are detonating right now. The universe is not a single isolated event. It is a frothing foam of infinite realities, a multiverse, where the laws of physics themselves might be different in every bubble. In one, gravity might be too strong for stars to shine. In another, electrons might not exist. We can never reach them. The space between our bubble and the next is stretching too fast. Our universe is just one bubble among many, separated from the others by regions of space that are expanding too fast for us ever to cross. And the story is still unfinished. Newton's gravity once cracked Einstein's static universe collapsed, and now even the inflationary Big Bang model shows signs of strain. As we step into 2025, astronomers are confronted with the Hubble tension, a statistically unbelievable disagreement over the rate of cosmic expansion. Measurements from the early universe taken from the cosmic microwave background do not match the values we derive from supernova observations in the modern universe. The gap is real, and it is growing larger each year. It seems the universe is preparing to break our models once again. We are standing on the edge of another revolution, realizing that even the multiverse might just be a small part of a much larger, stranger mechanism. We have climbed through 3 torn models and reached a view far wider than the one we began with. But the map is still incomplete. We began this journey in 1687, confident that we lived in a static, eternal safe haven. We were wrong. We moved to 1915 believing gravity was a force and the universe was fixed. We were wrong. We arrived in 1965 thinking we had found the singular moment of creation in a hot, dense bang. And once again, we were wrong. The history of cosmology is not a collection of truths. It is a catalog of our most brilliant failures. Each model was a map that guided us for a time, only to be burned when we reached the edge of the territory it described. The inflationary Big Bang is the best map we have today. It solves the paradoxes of the horizon, the flatness, and the missing magnetic monsters. It explains the seeds of the galaxies and the architecture of the vacuum. But if history has taught us anything, it is that this map, too, is incomplete. The Hubble tension is already tearing at its edges, whispering that another revolution is coming. We are not at the end of the story. We are barely past the prologue. We have realized that our observable universe, everything we can see, touch, and measure, is likely just a microscopic bubble in a frothing, eternal ocean of realities. We are not the center of creation. We live in a small, temporary region of order inside a much larger and possibly chaotic multiverse. So when you look up at the night sky, do not see it as a static painting. See it as the aftermath of a violent, silent expansion that is still echoing around you. The Big Bang was not the beginning. It was simply the moment we woke up. But if this wasn't the true beginning, then where does the story really start? The first page of the universe may still be missing. That is a question for another time.